Hello, everyone. So, in your differential equations, probably you have seen that if you have a linear ordinary differential equation with the forcing function on the right hand side being an exponential function, a harmonic function, or a polynomial, there are some general forms for the particular solution of that ODE, right? So, for example, let's say I have a massive spring damper system, or I have an RLC circuit, correct? So here, this is my voltage source, and then I have a resistor, capacitor, and an inductor all in the circuit in series. So this is my inductor L, this is my resistor R, and this is my capacitor C, and this is my V in versus time. Okay, and this is I, the current in the circuit. And then you want to, let's say, measure I or measure V out, any of them. And you want to see for a specific V input, what is going to be the I or what is going to be the V of output, which you can get from the two ends of any of these elements or a combination of them. So for example, if I focus on I here, I have the voltage across these three elements, sum of it should be equal to Vn, correct? Based on the Kirchhoff's voltage law, or you can write it as Vn minus L di over dt, then minus R times I, and here assuming that the elements are linear, minus 1 over C integral of I dt, correct? This whole thing is equal to 0. And now, if you want, you can take a time derivative from both sides, correct? And if you do, then you will get d of V in over dt is equal to L second derivative of I with respect to time plus R first derivative of I with respect to time, and then plus I over C. And here, if the goal is to find I of t given a specific Vn of t, then you're solving for a second order linear differential equation, correct? So let's say here I give you Vn and I give you two initial conditions, like what is I at time 0 and what is the derivative of I at time 0. And my question is, you give me back I as a function of time, correct? So if you know from your differential equation, the solution here has two parts, a homogeneous part and a particular part. And your homogeneous part is, if you consider the left-hand side, which is only a function of time here, to be 0, that gives you the homogeneous solution. And then if you consider this term that is non-zero, then that will give you the particular solution, and you add them together. Okay, now for the particular solution, the form of this particular solution does depend on what? On this function. Now, if I call this function whatever you want, let's call it f of t. As I said, if this f of t is an exponential function, or it is a polynomial function, or it is a harmonic function. If it's any of these or combination of them, then finding the form for this particular solution is not hard, and you can do it based on the forms of these and the roots of the characteristic equation, which comes from basically setting the left-hand side 0 and then forming a polynomial based on these derivative terms that you also would use for homogeneous. Good. Now my question is this: if this f of t is not any of these, okay, it's like a periodic function in this case, and this periodic function is not a form of a harmonic. So for example, let's say the function I give you, this f of t, is now going to be a sawtooth function. So now I have a differential equation like this, as I said, L second derivative of I with respect to time plus R first derivative of I with respect to time plus 1 over c times I equals f of t. And as I said, this f of t is a periodic function, but none of those three specific functions that you learned. So this is f of t versus t, and as I said, I want this function to be a sawtooth function, something like this. Right? Where basically the period of this function is any number that you want, t, and this magnitude is again any other number that you want, right? Some people might say 1 over t, it doesn't matter, it's just a normalization. So some magnitude, let's say a. So that's my function. A periodic function is a line basically with the slope of a over t between 0 to t, and then it goes down to 0, and then again it repeats itself. Or let's say it's a square wave. That's another case that you might have, correct? So let's say it is a square wave, which you see a lot in electric circuits. So it is something like this, right? It goes up, goes down, goes up, goes down, and it repeats itself. Now my question is, if I give you two initial conditions for I, can you still find I of t for me? For that forcing function? And the answer is, it's not that easy. Now, one of the solutions for it is called the Fourier series. So what we do, instead of using the original function, which is none of those three well-known functions, I try to write this function, approximate this function by a bunch of what? By a bunch of sines and cosines. How many of them? I'll show you infinitely many. Now, will I use all of those infinitely many? Should I keep adding these terms forever? No, we only need some of them, a few of them. But now, since these functions that I approximate my forcing function with are harmonics, I know the form for what? For this I of t for them, particular I of t. And so I can simply, since the system is linear, I can find a particular solution to each one of them for this system, and then simply what? Add them together because the system is linear and I can use superposition. Okay, so that's the idea. Is there a way that I can write a periodic function in terms of a bunch of harmonic functions, approximate it? And again, that's what we call the Fourier series. So the Fourier series which is based on the name of the French mathematician Fourier, they said that if you have a function with a period of 2t or 2l or whatever you want to call it, so here this f of t is periodic with a period of 2t. which means that the value of f at t plus 2t is the same as the value of f at t. If that's the case and some other conditions are valid for function f of t, what are those conditions? I don't want to get into a lot of depth for them, but those guys are called Dirichlet conditions, or you might call it Dirichlet, but the actual pronunciation is Dirichlet. So if the function also satisfies these conditions called Dirichlet conditions, and there are three of them, that this function must be absolutely integrable over one period, and it has to be of bounded variation in any bounded interval, and it also must have a finite number of discontinuity, and those discontinuities should also be finite themselves. Okay, so there are three conditions. If you want, go search this. When you say absolutely integrable, means the integral of the absolute value of the function in that range let's say in any range from t to t plus 2t, this thing should exist. Okay, it should not go to infinity. We call it the function is absolutely integrable. Or if the function is of finite variation, means the function changes should not be almost like infinite. For example, if you consider the function sine of 1 over x, or in this case 1 over t, if I have a function like this, and if you look at this function, if you plot this function versus time, it is what? It is a sine function, but as it gets closer and closer to 0, let me show you a plot of that. It's not easy to draw it by hand, but I'll do my best. So you start here, and then so here is 1 and this is -1, and then it starts basically increasing the frequency of it, right? So you start and then it gets faster and faster and faster until when you get to 0, you almost have no x for a huge change in y, and you say this is now when it gets close to 0, bounded variation. In other words, the frequency of the signal goes to infinity. Okay, it changes that fast. So this function is not satisfying the second of the Dirichlet condition, right? And again, the function should not have the infinite number of discontinuities, and those discontinuities should not be infinite themselves. Okay, so if you have functions where they have basically a vertical asymptotes, correct? So you have a function that is like this, then here you have a discontinuity, but the value of it is infinite. So this function also does not satisfy the Dirichlet condition. So this Dirichlet conditions, there are three of them again, and as I said, if your function satisfies those, now you can write your periodic function in terms of what? Sines and cosines. How many of them? As I said, infinitely many. But we really do not need to go infinite, okay? So first of all, how do we write it? Well, we write it as a constant term A naught plus infinite number of harmonics. So they start with n of 1, they go to infinity, and they are like a constant an. Of course, it's not pure constant, it does depend on n, times cosine of n pi t over t, and then plus bn times sine of n pi t over t. Okay, so this is how you can write it. You clearly see it's infinite. Now, can I incorporate this A naught with these? Yes. Okay. If for the cosine term, I basically say n is 0 instead of 1, then it's going to be cosine of 0, which is 1, and this is going to be a naught. So this term is another one of those cosines when n is 0. But since I don't have, and I can include that if I want, because for n of 0, the sine term is 0. So if I want, I can make this n go from 0 to infinity and bring this a naught inside and just get rid of this constant term. So again, you can write it as pure sines and cosines and no constant term. By the way, this term we call it bias, okay, or DC value. And you can write it as just sines and cosines, okay? Now, clearly you see there are sines and cosines. Clearly you see as n goes up, the frequencies of these harmonics is increasing, because the frequency of this sines and cosines is this guy here, n pi over t, and pi and t are constant, so it depends on n, right? So the frequency of the first set is pi over t, the next one is 2 pi over t, 3 pi over t, 4 pi over t, and their frequencies are going up and up, okay? They are harmonics of each other. So that's what we have with increasing frequencies. Now this an and bn, as I said, they are not constant completely. They are functions of n. So these coefficients an and bn also are basically functions of n, and a naught is also, it's not a function of n, but it's a function of the f of t, integral of f of t. So let me include that as well here. So a naught, what is a naught? That's 1 over 2t, the integral from negative t to t, or 0 to 2t, right? So it depends on, it's over one period in general, depending on where your one period is. So let's say if your period for the function is between 0 to 2t, then it's 0 to 2t. If it's between negative to t, then you write it that way. As long as this upper to lower limit is one period, you can integrate your function over one period. And you know the meaning of this based on what you know, hopefully, in signals. This is called the DC value, or the average value of the function, or we call it the bias. So we call it the bias, or we call it the DC value of f. Okay, so that's a naught, and then an and bn are very similar. They have 1 over t, not 1 over 2t. And this integral is again taken over one period. But now, instead of f of t being integrated by itself, it is multiplied by those functions right in front of them in the Fourier series. So you see here an was multiplied by cosine. So here also f of t is multiplied by what? By that same term, cosine of basically n pi t over cap t dt. And this is sine of n pi t over cap t dt. Okay, so these are these coefficients, a naught, an, and bn. And I'm going to show you through an example how to calculate these coefficients. So here for function f of t, choose the rectangular wave. And here, so if I plot it for you, f of t versus t, again, the whole function could be positive, or it can go positive, negative, and I would choose that case. So what you will have is this function being some number between 0 to, let's say, 2 here, and then it goes down, drops, now goes to the negative of that number, and then goes back to the same level and keeps repeating itself. Okay, so let's say the period of this function is basically 4. So this number is 2, this number is 4, and you have a level here, 1 and let's say -1. And for this square wave, what you want to do is to basically determine the Fourier series. Let me write it, show it this way. Might be more visible. So I have to calculate an, a naught, and bn. A naught, based on the definition, is 1 over 2t, correct? And first you have to know t, and t is half of the period. 2t is the total period, which is clearly equal to what? 4 here. So t is 2 and 2t is 4. So it is going to be 1 over 4 integral from 0 to 4 of f of t dt. And remember that integral of f of t dt is the area under the curve over one period. And when you divide it by that range, okay, so this is what we call, as I said, the DC, the average or the bias of the signal, okay? If you want, you can also call it the average value of the signal. So what is the average? If I look over one period from here to here, the area under the curve is clearly 0. So this integral is 0, and if I divide it by any number, no difference, it is going to be 0. So a naught, the average value of the signal going from positive 1 to -1, if you draw average, the average is 0. So there is no bias in this signal because it's symmetric about the t-axis. But now, what about an? So an is 1 over t, and t is 2. Integral from 0 to 4 of f of t. And then cosine of n pi t over 2 dt. Now, when you integrate here, between 0 to 4, you can split this into two parts, which is between 0 to 2 and then 2 to 4. Okay, so if I continue here for you, this is going to go from 0 to 2, and then from 2 to 4. And in each one of these ranges, the function changes from +1 to -1. Okay, and you know integral of cosine is a sine function. By the way, this is a cosine. I'm sorry for the mistake. This is cosine. And here you will get 1/2 of, this is going to be, this coefficient comes out, it is going to be 2 over n pi sine of n pi t over 2, calculated at 2 and 0, and this is going to be basically -2 over n pi sine of n pi t over 2, again calculated at 4 and 2 subtracted. So if I continue here at 2, this is going to be sine of n pi at 0, that's 0. So this is going to be sine of n pi minus sine of 0. That's for this. The other one is going to be sine of, if you plug in 4 here, it is going to be 2n pi minus sine of n pi. Okay, so you know sine of 0 is 0. Sine of n pi for any natural number n times pi, 1 pi, 2 pi, 3 pi, they're also all 0. The same thing happens here, and 2n pi. everything is 0. So the answer is going to be 0. So cosine for here, it is going to be 0 coefficient behind it. ANs are all 0. A naught is even 0. What about BN? So for BN, I have to repeat the same thing, but with sine function. And I'm going to write the integral already split in two parts. So it is going to be 1/2 an integral from 0 to 2 of f of t sine of n pi t over 2 dt, and then integral from 2 to 4 of the same thing. Okay, let me do a little bit of cleaning here and making it nicer looking. And again here, these are 1 and -1. And if you do it, again, this 2 over n pi comes out, and you can simplify it with 2. So if you simplify it a little bit further, you will get 1 over n pi times. Now, the integral of sine is negative cosine, so it is going to be negative cosine of n pi t over 2, calculated at 2 and 0, and then minus cosine, so it is going to be positive cosine of n pi t over 2, calculated at 4 and 2. And so here, if you plug in, you will get negative cosine of n pi, and then positive cosine of 0. And then here is going to be positive cosine of 2n pi, then minus cosine of n pi. And you know, cosine of 0 is 1, cosine of 2n pi, so 2 pi, 4 pi, 6 pi, this is all 1 again. And then cosine of n pi in general, it can be written as -1 to the n, okay? So if it's 1 pi, cosine of 1 pi is -1. If it's 2 pi, it's +1, and so on. And the same thing for this. Okay, so this is 2 minus 2 times that, and the 2 can be factored out. So it is going to be 2 over n pi times -1, or 1 minus -1 to the n. Okay, and that's all it is, which even if you want to simplify it in terms of n, when n is even number, it is going to be 0. When n is an odd number, it is going to be 2. So it's going to be 4 over n. So if you want, you can write it like this: 0 and then 4 over n pi. This is n is an odd number. This is n is an even number. So your function f of t will be summation n from what? As you can see, from 1 to infinity of only bn sine of n pi t over t. But if you look at here, we said that for odd numbers, you have what? 4 over n pi. For even numbers, we have 0. So yes, here you're going to say it goes from 1 to infinity, but it should exclude even numbers. So it is going to be like 1, 3, 5, and then so on. Or you can write it as, if you want, 2i minus 1, correct? So you have to make sure it only includes odd numbers. And when that's the case, this is going to be 4 over n pi times sine of n pi t over, and cap t is 2, so you write it this way. So this is your function, and if you want to expand it, it is going to be like plug in 1, you're going to get 4 over pi sine of pi over 2 times t, and then plug in 3, you're going to get 4 over 3 pi sine of 3 pi over 2 times t, and then 4 over 5 pi sine of 5 pi over 2 times t, and so on and so forth. Now, a few important things. One is, if you look at the frequencies are increasing. Okay, so this is 3 times the previous one, this is 5 times the first one, and so on. So the frequency of the harmonics are increasing, but on the other hand, if you look at the coefficients on them, the magnitude of the coefficients are decreasing. This is pi, 4 over pi, this is 4 over 3 pi, 4 over 5 pi, and so on. So the magnitude of this coefficient, clearly, when n gets bigger and bigger, it is approaching 0. That's why, as I said, these harmonics, although you have tons of these harmonics, really infinitely many, they do not all contribute the same weight, the same amount to the function. Higher frequency harmonics, they have way smaller weight, and their contribution to the function is smaller. So it's only really the first few, and by few here it depends on the function, like 3, 5, 10, 12, 20 harmonics that have a significant weight, and the rest of them, they play small and smaller role in forming the function. Okay, so if you want to approximate the function now, you don't need to keep calculating this series forever. Maybe like the first 5 or 10 or 12 terms would be sufficient. Okay, and I'm going to show you that first through a MATLAB code. So here I just wrote this code, and I have this bn's basically written as a function, an anonymous function in MATLAB based on t and n. And the original function is 1 for t less than or equal to, and it's -1 for t bigger than 2. And I have a bunch of t values between 0 to 4, 100 data points. So I plot the original function, and then since a0 and an are all 0, all I have is bn, correct? Bn times sine of n pi t over cap t, which is all of this that you can see. And I evaluate this for different values of n, correct? So one time I do it using only the first term. Next time I do it using the first 2 terms, then the first 3 terms, and so on and so forth. And each time I show you that by adding more terms, you are getting closer and closer to what? To the original function. And how far do I go? Only 20 terms. Okay, so that's all I do. And let's take a look at it. So the blue thick curve is the underlying function, and you see here I'm changing the total number of terms I'm using from 1 basically all the way to 20. And you see, as I'm using more and more terms, the total approximated function is getting way and way closer to this square wave, correct? Now, a few things is, let me run it one more time so you can see it, is one is, as the number of harmonics increases, the amount of ripples in the flat areas, in the plateaus of function, is increasing. But this sudden change, this step type behavior that the approximate shows, is getting closer to what? To the original step type behavior. Okay, but at the expense of getting more and more ripples, because you have more and more frequencies added to your approximation. Now the question is, how far should I go if I want this red curve, which is the approximated function, to perfectly match this step type behavior? The answer is you can never do that. You need really infinitely many terms to get this perfect theoretical drop. We call it the step type behavior. It's not possible, okay, to catch this. And how far do I go before these ripples are kind of flat in this plateau? Again, that's infinite. So you can never get this approximation to visually be perfect like this. I can increase my number of terms here. Instead of 20 terms, I go 40 terms, and I can get closer and closer, but not perfect, okay? And you might say, well, you said only a few terms are needed to match up the original function. By match up, I don't mean exact match. I mean getting close enough. Now, I said how many terms you need, it depends on the underlying function. If your underlying function has sharp corners like these, then you can never catch them. So because you are using sine and cosine functions, and sine and cosine functions are smooth functions. They are not really having any sharp corners. So by adding a bunch of sines and cosines, you can never catch sharp corners. It's impossible. You can only get close to them. But if your function is a smooth function, like a sine function, cosine function, or not sine or cosine, but any function that does not have, because sine and cosine are already your basis, if your underlying function is a smooth function, then you do not need tons of these. As long as the magnitudes of these ripples is negligible for your application, then you can say, well, that's good enough for me. Okay? Also, on these corners, we have this ringing effect that I don't want to get into depth of that, but again, know that the more sharper corners your function has, which means it doesn't have derivatives at some points, the higher number of terms you need to match it. Okay, so that's one. The other thing, if you saw here, only each 2 terms when you jump, it shows a change. So you look, 5, 6, 7 is this, 8 doesn't change, 9 it changes, 10 doesn't change, 11 changes, right? 12 doesn't, 13 does, 14 doesn't, 15 does, and so on. Why? Because if you remember, we said that really it's only the odd terms that make a contribution. The even terms they don't. So if you go from 1 to 2, that's the same as you just stayed at 1. If you go 3 and 4, 4 doesn't do anything, it's only 3. So that's why you see here that it's only one of the 2 consecutive terms that plays a role, right? So when I go from 2 to 4, it's just 1 jump, not 2, correct? Let me show it one more time to you. Look, when it goes from any odd number to another odd number, the even number that you pass does not show any change. Look, 3, 4 doesn't do anything, 5. 6 doesn't do anything, 7. 8 doesn't do anything, 9. You see? So that you clearly can capture that here. That's one thing. I mentioned the sharp points that you cannot ever perfectly capture. And the smoother your function is, the fewer number of these terms that you need. Let me tell you one more thing, and then we go back to our original problem of solving the differential equation when this forcing function here is something like this wave. And I have some other piece of code, by the way, that I wrote, and this one is for a general function that you can have. You can have, like, if you want to model this step type behavior, you have to use, if you want to use the symbolic toolbox, which I used here, You can use the Heaviside function, but here, to make it different, I want to show you the sawtooth function, okay? F of t equal t, and I only go from 0 to 2 pi, so here I assume the period of the sawtooth function is 2 pi. And here I'm using my symbolic toolbox. I'm not using the inline or anonymous function. I'm using symbolic toolbox. So instead of me calculating the a n's, b n's, and a naughts first on the paper and then plugging numbers for them, what I do here, I let MATLAB do those integrals for me. Why? Because the command int in MATLAB can perform analytic integrations. So here I define my function, I define my range, and then these a naughts, a n, and b n, the formulas for them are done what? The calculations for them are done analytically using the int command, and then later using the eval command for different n values. I'm going to replace them, right? Replace the frequency n and keep doing that here. So again, I'm going to do the sawtooth function, and I'm going to use up to 20 terms and show you again when I add more and more terms, the effect will be what? Will be that your approximation is going to be closer to the underlying function. So let's take a look here. Okay, so here you see I'm using more and more terms, and I'm getting closer and closer to the line with the slope of 1. Okay, now the slope can change to anything you want. But clearly you see more ripples, but I get closer and closer. Again, at the end, it's impossible to match the sudden drop that goes down and then goes up again. It's impossible, but I'm getting closer and closer. And as I said, in this case, if I say an, it is what? It is a function of n. It is calculated by MATLAB, not me. And if you want to see it better, you can use the command predi. Okay, so I have an. If I want bn, I can have bn. If I want a naught, I can have a naught, and so on. Okay, so if you use this code, you can do it for any function, and you do not need to calculate any of these integrals by hand. So these are some MATLAB demos I wanted to mention. One other thing I want to mention is orthogonality. So you might wonder why, out of all these different functions in Fourier series, why is it that Fourier picked the sines and cosines? Okay, one major reason is the sines and cosine functions, they have a property we call orthogonality. In general, we say f of t and g of t are orthogonal over a range of a to b if the integral from a to b of f of t times g of t dt is equal to what? 0. Okay? For two vectors, we said the vectors are orthogonal if the dot product is 0. For functions, if the integral of the product of the two functions is 0, we say they are orthogonal. By the way, there is a notation. You might also show this as the dot product of ft and gt. Okay, so some people will show it with this notation. But you can show that sine and cosine functions are this orthogonal ones. In other words, you can show that the integral of sine of nx times cosine of mx, where m and n in general could be any number, but in this case we assume that they are not equal. If you integrate these to the product of these two functions from negative pi to pi over one period, or if n and m are bigger than 1, it's definitely more than 1 period. This guy is equal to 0 for n not being equal to m. Okay? And not only that, even that's the same thing for the sine function itself. So you don't need to multiply sine by cosine if you go sine of nx times sine of mx dx. By the way, here I have a dx term, so let me fix it. This is also 0 if m and n are not equal. Correct? And the same thing can be said about the cosine. So the cosine also with different frequencies, cosine nx and mx, if you integrate them over negative pi to pi and integrate this for m being not equal to n, again, the answer is 0. So that's why we call that sine and cosine functions are orthogonal to each other in the interval of negative pi to pi. And this orthogonality makes them suitable for being what we call the basis for the Fourier series, so that we write everything based on them. Okay, so that's why, again, we call sine and cosine orthogonal to each other. That's one of the reasons they picked them. And the other thing is they have a clear single value of frequency. So this is the frequency of the signal, this is the frequency of the signal. If you have a single harmonic, the frequency content of that signal is a single number, m or n. If you have a function like this, square wave, then the frequencies existing in this signal, there are basically infinitely many of them. And those are basically these numbers, n pi over t with increasing n. So you have tons of harmonics that you have to add together to make that signal. It means the frequency content of the signal is basically infinitely many frequencies, while here you only have one single frequency. So if you want to do frequency analysis, which is a little bit beyond this topic, then sine and cosine are extremely useful for that purpose. Okay, now going back to my original question to finalize this video is the ODE I had was L second derivative of I with respect to time plus R first derivative of I with respect to time plus 1 over C times I was some f of t. Okay, and as I said, let's say this f of t is that square wave. So I can write this as what? Summation n goes from 1 to infinity and only with odd numbers of what? It was, let me go back and check it. So it was 4 over n pi. Sine of n pi over 2 times t. Okay, so I can write my square wave like that. Now, if I come up with some numbers here, so let's say, for example, this number is 2, this number is 3, and this number is 1. And again, the goal is to find I as a function of time with some initial condition. How do I do that? I particular, especially, that I'm interested. So what do? I say, well, if I expand this, as you just saw, the expansion of this was 4 over pi sine of pi over 2, and then the rest of it, correct? So 4 over pi sine of pi over 2 times t, and then plus 4 over 3 pi sine of 3 pi over 2 times t, and so on. And let's say my application says, based on the accuracy I need, I don't need to go this forever, so maybe I only go up to let's say 20 or something, right? And the number right before 20 is 19. So I end up with something like 4 over 19, correct? 19 times pi, of course, sine of, and then here I have 19 pi over 2 divided times t. So instead of going forever, I approximate my function by what? Going from 1 to 19, or basically using 20 terms because 20 does not contribute here. So I only use basically what I have here, about 10 to 11 terms. Let's say those are enough to give me a very good approximation of my square wave. Now, if I look at each and every one of these, now I have only what? A sine. And if the right-hand side is a sine function, based on what you know, finding what? The particular solution for that specific sine function should not be a hard thing, correct? So this is going to be like a constant a, right, times sine of the same frequency, t, and then plus b times cosine of the same frequency times t. Where this a and b, how do you find them? You plug them into this equation, okay, and set it equal to this right-hand side, and then you try what? To find a and b, okay? You know that from differential equations, so I'm not going to go there. And then you move to this one. So if I call this IP1, then IP number 2, or you might call it IP number 3, doesn't matter. It is, so let me call this 1 and 1. Then this is going to be like A2 times sine of 3 pi over 2t plus B2 cosine of 3 pi over 2t. And again, A2 and B2, you plug them into the governing ODE with only right-hand side this term. And then you find A2 and B2 and so on and so forth, correct? So you find all of this all the way to IP9. In this case, it's going to be, I assume, 10, right? So that number 10 is going to be a 10 times sine of 19 pi over 2t plus b10 times cosine of the same thing. And again, A10 and B10 you will find from the plugin for the last one. And then your total solution IP of T, the particular solution, will be what? Will be summation of all of these IPs. Why? Because the system is linear and I can do superposition. So that's my particular solution, my homogeneous. I can do it. I just set my right-hand side to 0, and then I add them together, and my total solution will be homogeneous plus this particular. Okay, and that is going to be a very good approximate analytical solution to my what? To my differential equation, okay? And that's what you will use in vibrations, in controls, and many other courses when you're trying to deal with ODEs where the right-hand side is not a polynomial, it's not a harmonic function, or it's not an exponential, but it is a periodic function for which the Fourier series exists, and you can approximate that function using what? Using a bunch of harmonics, okay? So hopefully this was useful for you, and I will see you in the next lecture.